do this stuff.
Read books, school, workout.
Yeah, I get lazy with the reading. But I did start this semester, and then I got busy with like all my classes, and I was like, okay, maybe not. But next semester I'll probably do a few readings. I do want to.
Read Mein Kampf, the first book.
What book?
Hitler's book, Mein Kampf. It gives you an idea.
There's notes in every single one.
This is so nice. Good morning, sir.
Morning.
Look at the test practice. I think if he got us engine, he's gonna get you a fridge.
Fridge. We're engine to the right.
He give us. It's weird because he give us only 3 things. So basically, what happened is with us is like he gave us an engine that first of all same volume, triples in volume,
That was
right?
the one that was in the...
Yeah, but then it goes down, and it goes down again by having the double amount of triple amount of volume. Fucking shit! Why is it strength again? It had a beat, you know that is added, and then constant. So basically, it tells you isoboric, and then it increases. You know, not adiabatic, not everything, but it's low in temperature. So this is adiabatic, and then isoboric, and then it stops. He only tells you that it starts with the temperature and then goes back to it again. So you know that's
Okay, so some of you are obviously still taking the exam this afternoon, and we'll close out that. And I have made homeworks 9 and 10 available for you already. I expect to finish off almost all of homework 9 today, especially the stuff that is more heavily featured and heavily computational. Maybe a little bit of cleanup on Monday, but that's it. But that is not due till the Monday after Thanksgiving, if I remember correctly. If I'm not, then obviously do whatever says WebAssign. And the reason why I did that was because for those of you that may be choosing to do any of that over the Thanksgiving holiday, of course it's up to you if you want to knock it out beforehand. But if you do end up doing anything over the holiday, we want you to have access to in-person help. So that's why I don't have it due until Monday. You can ask me Monday when we return. However, I do want to caution you to not be last minute about it because homework 10 is due later that following week. I have it due on the Thursday after Thanksgiving. And the reason I've done that is because I really need you guys to have done a little bit of preparation for that homework, mirrors and lenses, even prior to that deadline because the mirrors and lenses lab hits that week. So that will be the lab that you do. In fact, it's your very next lab. We won't have lab next week because of the holiday, so the following week, the week of return, you'll do your mirrors and lenses lab. And the mirrors and lenses lab, you need to have done your homework at least in part, and you need to certainly have watched at least a good part of the lecture videos in order to be able to do that lab. Otherwise, that lab is going to be pretty much miserable to impossible to complete within that lab period. So that homework, again, it's due the day before the Friday lab. It's due the day after the Wednesday lab. To get you Wednesday lab, folks, just make sure that if you are planning to go home after the mirrors and lenses lab and start that homework, then that's not going to be a good strategy, okay? I expect we'll probably be able to get to about 10 homeworks total, so you'll have one more that's due the last week of classes. Okay, so right now all the homeworks except for the very last one are out there ready. In fact, I'll probably start, oh, sorry, I think I'm at homework 11. Yeah, so it'll be 11 total homeworks. So homeworks 9 and 10 are up already, and then 11 will catch everything else that we talked about. I might already be moving to that stuff next week because I don't have that much left to do with homework number 9, and homework 10 again is completely flipped classroom. You'll do that on your at home. So that's kind of the logistics looking to the end of the semester. Also, for those of you that are doing honors projects, time is running out quickly here, so hopefully you are going to take a serious look at that stuff shortly after you've cleared this exam, because there's not very much time left. I do need to have checked off your project by the end of the regular instruction, okay? Okay, any questions before we jump in? Okay, so here's what we're working on. Mainly working on refraction. So here's the deal. We have an incoming light beam interacting with a surface. Some light generally bounces off, reflects. Some light passes through. And this is the law called Snell's law. Basically, the gist of it is that it's like the product of n and theta is kind of conserved, sort of. So there's a sign thing that obviously makes the relationship slightly different in practical terms. But essentially, if you're going into a higher n, you go to a lower theta. So if you go to a higher n material than you're in before, you bend toward the normal. And vice versa, if you go into a lower n material, you bend away from the normal. So that's kind of the conceptual stuff that should become second nature. And I want to add to that statement that if the n values are, if the n difference is greater, then the bending will be greater. Question?
What if the molecule has a lot, like so much n that the light can't penetrate it?
Right, so we are here talking about optically transparent. So the light can't continue, the light is not absorbed. That's called attenuation, where light actually gets absorbed by the material. So we're not going to look at that much at all.
But can the light like go through a material and not come out of it?
That's what I'm talking about.
Oh,
so
okay,
if it gets absorbed by the material, we call that material kind of opaque because it doesn't allow the same light to go all the way through. We're not going to look at that. So these are transparent materials. If the n difference is greater, the bending will be greater. Okay, so we said that if you go to a higher n, you bend toward the normal. If you go to a much higher n, you'll bend more toward the normal. If you go, we said that if you went to a lower n, you bend away from the normal. If you go to a much lower n, you'll bend way more away from the normal, okay? So, likewise, if the n values are really similar, then the bending will be minimal. And if the n values approach the same value, you won't bend at all. As far as light's concerned, you didn't really actually go into a different material whatsoever. So if you have one material and another material, and these are the same, you won't bend whatsoever, okay? So as far as light's concerned, they're the same. I can give you a few examples of that. If you have something that's transparent, like say glass, right? Why are you able to see, say, a glass cup that you're holding in your hand? Well, the reason why, even though light passes through it, is you're not really seeing the glass unless it's, kind of dirty or whatever. What you're seeing is whatever is behind it, the light is being bent. So as light comes from behind the glass from something else, and it bends, you of course see a warped version of what's behind it. Now, you may be unconvinced that you couldn't see a glass otherwise, so let me take another example, air. Right? Air is completely invisible. You can't see air. But imagine, you've all seen this, maybe above a campfire, maybe above a match, maybe above a radiator, okay? You've seen kind of the shimmering, okay? That's not necessarily smoke. Radiator would be a better example because it's obviously not giving off smoke. It's just hot air. And hot air has a slightly different index of refraction than cold air. And so when you see something behind it, you're seeing that light getting bent in unexpected ways. And of course, it evolves with time. So you see that shimmering. Okay? So that's how you're able to see transparent things, is by the fact that light travels through them and gets bent. And you can see that. So in the drinking glass analogy, if you are the type of person who, when you do your dishes, you don't waste water by running the faucet, you just fill up your sink and you wash it all in there, right? Pro-environmental way to do your dishes, okay? It can be very hard to find a drinking glass in water. And the reason why is because light traveling from water to glass, it's a much smaller change in the index of refraction than it is from air to glass. So you can be like, where did I just put that glass in here, where did it go? I can't find it, okay? It's very hard to find things made of glass or clear plastic underwater for that reason. Now you can take this to its absurd extreme and get a material that has an index of refraction that is not only close to glass, like water, but exactly the same as glass. And then you can literally get something to disappear. And on your homework, I included a photo of such a thing. I put a glass dropper into a material which is an oil, which happens to have almost identical index of refraction to the glass, and you can literally see it disappear. It's an essay question. It's worth 0 points. I just wanted to show you the photo, okay?
It's the last question on home. I saw it.
Somewhere, I don't remember, but it's a picture of basically you're dropping a glass eyedropper into a special oil, and it completely disappears because it's not just minimal bending, it's no bending. Okay. I guess. So this is the kind of stuff that I need to talk about what I sort of demoed at the end of last time. So I didn't have to bring the demo back. Total internal reflection, or TIR for short. So let me just remind you what this was. Generally speaking, you can have both a reflected and a refracted beam, but under special conditions, you will have only the reflected beam, so total reflection. So basically how this happens is the following. If you have n sub I and n sub t, and I specifically have a smaller n value on the outgoing side. So I have my incoming beam, and I'm going to increase that angle. So the reflected beam, of course, we said that you reflect at equal angles, so that's going to get bigger. And because you're going into a smaller n, are you going to bend toward or away from the normal again?
Higher, towards.
Towards, that's right. So smaller n, higher theta. So it's going to look something like this. So this is theta t. And as I increase the incident angle, I'm going to increase the refracted angle. Now because the light bends away from the normal on the refracted side, we wind up with an interesting possibility where the theta sub t being always larger than theta sub I, at some point before theta initial gets to 90, this will get to 90, okay? So since n sub I is greater than n sub t, that's necessary for this phenomenon to happen, we have that the transmitted angle is greater than the incident. Therefore, this can go to 90, but while this is still less than 90. So, we can draw this. Once this has become big enough, theta sub I, you'll have a reflected beam and theta sub t has gone to 90. And I guess I should draw theta r as well. Okay. So what we have, I guess I should label the ends as well. N sub I, N sub t. So what we have now is that the refracted beam is this weird thing that skirts the limbo between the two materials. Okay, it doesn't really actually make it out into the N sub t anymore. And this is where I have to tell you that rather than live in the limbo between the two materials forever, it chooses instead to die. So this is actually a beam that ceases to exist. So again, we cannot, it's a little beyond the scope of the class to compute the percentage of the intensity that goes into each beam. But here's the thing. As this angle increases, it turns out the intensity is decreasing. And by the time it gets into this limbo where it doesn't get into the second material at all, it actually takes the opportunity to not exist at all. Turns out that 100% will go into the reflected beam. So this is why it's called total reflection, because now the light is 100% reflected. The refracted beam doesn't exist. And the reason why it's called total internal reflection is because oftentimes this is some kind of internal environment like a material, and N sub t is often the outside environment like air. Okay? So let's work out the math of this. We'll put down a refraction law. What you can see is that this is not going to happen automatically because N sub I is greater than N sub t. You also have to go to a large enough angle. Okay? You have to have that theta sub I is large enough so that theta sub t, bending away from the normal, bends all the way to 90. So that minimum angle is called the critical angle. That's the angle at which the outgoing beam bends to 90. Okay? So we can solve here for the critical angle. This is the expression for it. So ironically, the N sub t, which you never actually go into, is still a factor in the equation. This is the material that you're trying unsuccessfully to go into. So you still have to factor in the properties of a material that you actually never go into. Now, if that seems weird, let me point out that if there wasn't a interface between two different materials, you would never have had a reflection in the first place. The light wouldn't just spontaneously reflect inside of material. You need the border line between the two materials to initiate the reflection. Okay? Now, you can, of course, solve this for theta sub c and solve for it, but then you'd have an inverse sign on the other side, which I think looks ugly, so I'm going to leave it like this, right? If you ever actually want to solve for it, take the inverse sign on both sides. Now, that is the critical angle. That's where the party starts, okay? However, as I showed you in the demo last time, that once you've gotten to that big of an angle, you'll never get back that refracted beam. So in fact, total internal reflection happens for any incident angle that meets or exceeds the critical angle. The critical angle is just the minimum angle. It's where the party starts. But any angle bigger than that, and you're still going to get total internal reflection. So the critical angle is just like the minimum bar that you have to climb over for this phenomenon to start. But it does occur for any larger angles as well. Okay? So remember the conditions for total internal reflection. First of all, it is only possible if you're in a higher end bouncing off a lower end. It's exploiting the bending away from the normal in the first place. You could never have this otherwise. So it depends when you're going to get total internal reflection. If you're in a higher end bouncing off a lower end material, and if the incident angle meets or exceeds this minimum bar called the critical angle, which can be solved for by this equation. So these are the basically the things you need to remember for total internal reflection. Okay? So, one of the things that I can point out about this equation, again, if we ignore the sign is not that interesting. Sine between 0 and 90 is quite boring. Basically, you can think of it as the critical angle roughly goes as nt over ni. Okay? Now, nt, as I mentioned, is the outside environment, usually air, where nt is approximately 1. So if we talk about trying to get total internal reflection to happen, we can get a relationship between the index of refraction of the material and the critical angle. And what we see is that if the material itself has a higher n, it will decrease the critical angle. It will lower the bar you have to climb over. Okay? So if you're trying to achieve total internal reflection, if that's your goal, you want to lower the bar. Okay? So I think that analogy, that idiom, comes from the high jump or something, right? So if you have a high jump, would you rather try to clear a bar that's 7 feet tall, okay? Or would you rather step over one that's a foot tall, okay? So obviously, if you want to achieve total internal reflection, you want to use a very high index of refraction material because then it's relatively easy to clear the minimum bar. And that just comes from this. When the n difference is greater, the bending is greater. So for instance, if I had a fixed nt, like air, but I had a very, very large index of refraction of the material, I could come in at a relatively modest angle, and basically here, you can see I'm pretty much already at total internal reflection. The bending away from the normal is so extreme that I don't need a very large incoming angle to get a huge bend away from the normal and already get basically almost or even possibly to total internal reflection. Okay? So basically, with a larger n difference, it is easier to achieve total internal reflection. And when I say easier, I mean you have a lower critical angle. Does that make sense? So let's talk about materials. I mentioned when I was first introducing the concept of index of refraction that diamond has among the largest indices of refraction of naturally occurring materials that are transparent to light. So it's extremely easy to get total internal reflection in a diamond. Okay? So let's take a look. Now if you go into a mine somewhere and you dig out a rough hunk of diamond, it doesn't look very exciting, hence the saying, diamond in the rough. It's not exciting. If you want to actually sell it to somebody, you have to cut the faces and you have to specifically design the facets in a certain way. Let's kind of take a diamond example, and I'll do our typical cartoon diamond, the one that sort of looks like this. So someone has very carefully cut it in a particular way. So let's kind of walk through what we do. This is sort of analogous to many of your homework problems. I'm not going to do it with numbers because the general gist I think will be plenty. So let's take a look at a light beam that goes in. So in this case, n sub I is the air, and n sub t, where it's going to, is the diamond. So there are two reasons, not one but two reasons, why you don't get any total internal reflection here. Can anyone tell me one of them?
Air is less than diamond.
Orthogonal, yes, so along the normal, right? You're not making a large enough angle. Remember that when you don't even have any bending unless the angle is greater than 0. So that's one reason, is that you're coming in at too small of an angle. And what's the other one?
And I is too smaller than NT.
That's right. Ni is a small one, NT is a big one. So there is definitely not going to be any total reflection here. Some light is going to get through, and that's the light I'm interested in, so I'll chase that. I'll give up the reflected beam simply because I'm just chasing the ray of interest. So I want to chase the light that gets into the diamond. Okay, so now we're in diamond, so that's n sub I, and we're interacting with potentially going back out into air. But now you can see that the facet of the diamond is cut such that you will come in at a perhaps substantial angle to the normal. And because the end difference between diamond and air is so great, the critical angle, the minimum bar you need to climb over, is not so big. And if this angle meets or exceeds the critical angle for this situation, you will not get any light that comes out. It will 100% be reflected. Looks something like this, equal angles. So attempt number 1 to get back out of the diamond has failed. We have achieved total internal reflection, and we'll do it again. You can see now why these tend to cut the facets of the diamond the way they do. They're trying to encourage total internal reflection. And once again, attempt number 2, this is designed so that the incident angle meets or exceeds the critical angle. So you will again bounce off. And we get to attempt number 3 to get out of the diamond. Are we going to get out this time?
Yeah.
Yes, because we're going to come in basically 0 degrees to the normal. And so 3rd time's the charm, you get out. So this diamond has managed to take the light that went in and shoot it essentially right back at you. We call this the twinkle of the diamond. That's part of what adds their value, okay? Now you probably know that diamonds twinkle in the sunshine, diamonds do not twinkle in the dark, okay? They do need a light source. They are not just glowing by themselves. The way that a diamond twinkles is by taking light that goes into them, and because the way the facets are cut the way they are, it bounces them back up at you in unexpected ways, and you go, ooh, shiny, okay? And when they tell you to shop for diamonds, they always say, don't look at it on some horrible fluorescent light, go out in the sunshine, because the light that comes out is only as good as the light that went in. It's just taking what got sent in and bouncing it back at you, okay? Are there any questions on that? Yeah?
Can you trap a light inside a diamond? No, you can't, right?
Well,
It's
at
too
some
fast.
point, right, it would be difficult to get this to keep going and never ever make an angle, no matter what it hit, that was smaller than the critical angle.
Put a light beam and close it.
Now, I can show you a way to trap a light indefinitely, but it's not with a finite hunk of diamond. Are there any questions on the nuts and bolts of this before I do another example? Yeah.
Where is the critical angle?
So the incident angle just is what it is based on the geometry. But the critical angle, you can compute it. You would put in NT is 1 for air and NI is whatever for diamond, 2.62 or something. And that's the critical angle. And that is the, let's say that came out to be, I don't know, 40 degrees. That means if your incident angle is 40 degrees or higher, then you'll have total internal reflection. It may not be that low, but 70 degrees or 75 degrees, whatever, these are all things that will cause total internal reflection. So the best way to attack these problems is just do some geometry to figure out what the incident angle is, just from the situation, and then compare that to the critical angle, and if, again, the angle that you found is bigger than that, you will get this. So anything that's equal to or bigger than the critical angle, you will get this. Does that make sense? Any other questions on the diamond example? Okay, so let me show you a fiber optic cable. Also works on this principle. Something like this. We have N sub I is the fiber optic cable, and then the outside environment smaller. So, fiber optic cables, if you go on to, a website in Europe and it takes you like fractions of a second to get that information, that's because you're getting that through a fiber optic cable. So we're exploiting the fact that light moves extremely fast, and that's how you can get that information so quickly. There are fiber optic cables that are laid down on the ocean floor, and that's where you're getting your info. Okay? So how does this work? Well, if you have a light beam that you shoot into the cable, you drop your normal here. That's your incident angle. If that incident angle meets or exceeds the critical angle, then none of the light will leak out. So nothing gets out. It'll be 100% reflected. Now the cool thing about this geometry is that you don't have to micromanage every single bounce that the light has with the interior wall of the cable. You can see that if I manage to do it on the very first bounce, you can see that the incident angle will be the same every single bounce, right? So if this angle meets or exceeds the critical angle, well, this is the exact same angle, right? The geometry of the situation is that those are the same angles. So whatever angle you hit the inside wall the first time, that'll just be maintained all the way on down the line. The angles are the same. So in this way, you should not lose any of the light. You don't lose part of your intensity to the outside environment. If that fiber optic cable is laid on the ocean floor, what good does it do for some light to leak out into the water? Okay? So in this way, you can keep the light perfectly 100% trapped inside the fiber optic cable. I guess I forgot to label it. If you want to jot down, this is a fiber optic cable. Okay? So we don't really look at the fact that eventually when light goes through something, it eventually gets absorbed by the material itself. That's called, again, attenuation. So you probably know that if I had a thing of glass that was a mile thick, or a block of ice that was a mile thick, you can't see through it after a while. So what happens is that it is possible for the light to be absorbed by the material itself and released probably as infrared. So the light gets absorbed, it makes the atoms jostle around more, and they tend to release it another way. We talked a lot about this. This is black body radiation, right? Black body radiation, it takes whatever comes in, including visible light, absorbs it, and then outputs it based on temperature. So we're not going to neglect that in this discussion, but you should be aware that if you have a fiber optic cable on the ocean floor, you can't just put you have to put what these things called repeaters every couple miles, which will take the weakened signal, the attenuated signal, read it in, boost it, and then send it on its way again, okay? So I don't want to sugarcoat the situation, like all you need is a glass fiber that runs from here to Europe and you send light through it, it's going to be just fine, okay? But the point that I'm trying to make is that the light will not leak out, okay? So the visible light that's bouncing off the interior surface, you will not have visible light that leaks. So I have a fiber optic cable here with me, so let's take a look. So this thing is transparent, okay? It's just a fancy piece of plastic, basically. You can buy this stuff. I think it's like, I don't know, it's like 30 cents a foot or something, or not even. It's really cheap stuff. And I'll have myself a little green laser, and I'll send it in one end, and comes out the other. See the little green tip? Now you can't see it for the bulk of the length of the thing, despite there's some damaged parts of it, but you can't see for the bulk of the length because if it doesn't leak out, then how are you going to see that? Okay? But it is all in there at all points. In fact, one of the things that I can do is I can bend this, and we should be able to see get the light to leak out because we lose total internal reflection. So if I can find a segment here it's hard to hold all at once.
You need help, sir?
So let's find a segment that looks pretty, doesn't look very green. Man, this cable has seen better days. But if you take a segment and you bend it, you can get it to go more green.
Yeah.
So you get more leakage. Oh, now I really damaged that part. It's leaking permanently. You see that? I lost total internal reflection right there. So I gotta get a fresh segment of cable because I've bent this too much in the past. So basically what I'm doing there is if I put a horrific bend in the cable, then when this bounces, the angle will be too small and it'll leak out, okay? So this will come out, and then you can see that it's green. Have any questions on that? So a lot of this stuff just requires a lot of geometry. That's why this is general field of studies called geometrical optics. And you can, when you're tracking what the light actually does, you can see what angle it makes to the normal and compare it against the critical angle and see if you actually get this, okay? If you get the total internal reflection phenomenon. Okay, so that's total internal reflection. Any questions on that? All right, so now let's tie together two topics we've been talking about. We've talked about reflection. We've also talked about polarization. So polarization by reflection. So my discussion of polarization previously was talking about this man-made, manufactured thing called a polarizer, but there is also, in nature, this phenomenon certainly occurs. So let's talk about this. So I'm going to draw my situation again with my typical 3 beams. And I've been drawing them as light rays for some time, which is to say I've ignored the waviness of the wave entirely. I've just drawn an arrow to indicate the motion, the direction of motion of the thing. Now I want to remind you that the light can generally be polarized. So let's say we have unpolarized light. So I've been generally drawing it like that in my kind of horrible 3D diagram. That's awkward because all of these are perpendicular to the direction of motion. It's a transverse wave. So I'm going to clean that up a little bit. So I'm going to put this right here. So that's the part of the wave that's going like this. And then there's also, of course, a polarization where it goes in and out of the page, like that. And I'm just going to draw that as a dot. Before, I think I was drawing it as an in arrow and an out arrow together. But let me just draw it as a dot, okay? So those are 2 perpendicular polarizations. And of course, if I have unpolarized light, I'll have all sorts of combinations of them as well, right? So everything can be resolved into components of these 2 polarizations. So this will be sufficient for my purposes. Let me give both of these polarizations a name. I'll call this P polarized, and I'll call this one S polarized. Let me tell you what those stand for. P stands for plane polarized. So P is for plane. So what plane do I mean? This light is polarized in the same plane as the incident, reflected and refracted beams. In other words, the plane of the page. I've drawn my 3 beams, incident, reflected, and refracted, in the plane of the board, and this is in that same plane. That's why I can draw it on the board. The S polarization is perpendicular to that entire plane. So S stands for perpendicular, which is the word I made up because perpendicular also starts with P, okay?
Oh my.
So I like to think of like a serpent. Okay. Okay. And so the reason why, by the way, it's called S is because in German, as the word that means perpendicular does start with S. I'm not going to try to pronounce it. Okay. But since we're doing this in English, you have to just have some sort of mnemonic to remember why S is the perpendicular polarization. So this is perpendicular to the plane of I, R, and T beams. So what we have coming in is unpolarized light. And so it, of course, has some P, some S, and every combination in equal amounts of P and S. Okay? So let's go ahead and draw it coming in. I'll draw a few more just because why not? However, we will find that it is possible that the beams that go out of this interaction with the surface do not necessarily end up with completely unpolarized light either. Okay? Generally, they don't. So let's take a look at why that is. So again, work up to where this phenomenon occurs. So I will increase the incident angle gradually. And I will, of course, that means I will be increasing the reflected angle as well. That's just the same angle. And I find that something very interesting happens when, let's draw the refracted beam. So we're not yet at the critical angle. We still do have a refracted beam that makes it into the material. The interesting thing where we have to notice that something very strange happens is actually when the two outgoing beams make a 90-degree angle to each other. Okay? And we notice something very interesting about that is that when the angle between the R and T beams is 90 degrees, we find that the light, the reflected light, is 100% polarized. And in fact, it's 100% S polarized. So while all polarizations went in, only one actually made it into the reflected beam. So I guess I could draw that. I should probably just have drawn it over here. So I guess let me say that I'm at this case. It's not too far off. These two make a 90-degree angle. And what you get out is this. So this is 100% S polarized. There is no P polarization in there. Now, common misconception is that because this is 100% S polarized, I'm not saying that all of the S polarization went into this beam. I'm saying that the only thing that made it into this beam was S. There is also some S over here. What has happened is that the P polarization has gotten blocked from this. Okay, so it's not that. So basically, the reason why this is 100% S is not because all the S went over here. S's get split between them, but the P was entirely blocked. So we'll find the P over here. Okay. So the refracted beam is actually a mix of S and P. we might not say that it's completely unpolarized. It might have a slightly different mix of S and P, but the point is that it still has both, okay? But this is now completely polarized. It's 100% polarized. Okay? Let me say a few brief words on why this is, for those of you that are in a position to understand it. If you remember, one of the things about in Physics 260 about shaking a charge. If we shake a charge, it'll make a wave that goes off like this, but it does not make an isotropic wave that goes off in all directions. In fact, over here, you don't make much of anything, okay? So the way to think of it is that if you want to put a wave on a clothesline, you have to move your hand perpendicular to that. You can't just go like this. Now that's a longitudinal wave, but that's a different story. We're talking transverse waves here, okay? And so that's exactly what happens here, is that this polarization comes in and it shakes the charge like so. And it shakes the charge like so, and it can put stuff in here. That's why the P polarization goes just fine in here, but because this is a 90-degree angle, this cannot be sent over here. In fact, if you sent only P polarized in here, you get the P polarized in here, and here you get nothing. So if you sent in light that wasn't unpolarized, but if it was just P polarized, you would get 100% refraction. You would get no reflected beam whatsoever because the P polarization is not allowed in the reflected beam, okay? So here, if this is only P polarized, you get 0% here and you get 100% here. We could call that total refraction if you wanted to. So essentially the reason why the reflected light is polarized, it's all S polarized, is because the P got blocked from that, okay? So we sorted out what was available in the unpolarized light, and some of it's allowed in here and some of it's not, okay? So a common misconception is that this splits the polarization into S and P. That's not quite right. Remember, the refracted beam is still a mixture of the two. It's that because one polarization is disallowed from the reflected beam, it ends up being all of the other, okay? Does that make sense? So I'll switch here to my regular picture here. It looks like this. And let's suppose that I had a horizontal surface, and I find that I get 100% horizontally polarized light. If you bounce light off a horizontal surface, you tend to get horizontally polarized light. So now we can talk about how sunglasses work. Okay, polarized sunglasses. What are you looking at? You're looking at the hood of your car, or the road, or a lake, or an ocean, all horizontal surfaces. So when sunlight bounces off of them, it tends to be horizontally polarized. So if you want to block that as much as possible, what should the transmission axes of your sunglasses be oriented?
Perpendicular to it?
Vertical, that's right. So we'll draw ourselves a nice pair of sunglasses here. That's how the transmission axes of a pair of sunglasses should be. And if you own a pair, try it sometime. When you're looking at the road or a lake or whatever, go like this, and you'll see it get much brighter because, of course, you're tilting your transmission axes to let that horizontal light through, okay? You can get the brightness of the road or a lake or something to change. Maybe some of you don't have polarizing sunglasses, but you have a filter on your, or a lens on your camera that does this. It's meant to take out this light. This is called glare. So glare is unwanted reflected light. Now, why doesn't your vision go completely black? Well, first of all, you're obviously getting some direct sunlight, which is unpolarized, generally speaking. but you probably don't spend your time staring at the sun. You probably look at things that reflect the sun. You probably also look at lots of other surfaces, which, because they're oriented differently, they're not giving you exactly the same polarization. And the biggest reason is that this phenomenon is only exact when these two have this exact geometry where these two have a 90-degree angle. In fact, this special incident angle is called Brewster's angle, and we're going to calculate how to get it just in a moment. But it should be said that even though this only occurs at one special incident angle called Brewster's angle, for a wide variety of angles around that, we still get highly polarized, highly S-polarized light, if not entirely S-polarized. So the reality is that most of the sunlight you're getting still does have a little bit of the P-polarized. So the way you could draw it is you have mostly S with a smidgen of P still mixed in there, and since that will go right through your transmission axes, you'll see that, okay? So even if you're looking at a spot on the road and you're going like this, chances are you're not going to be able to make it go completely black, because while the predominant polarization is S, only at one angle called Brewster's angle is this an exact result. Okay, so while I have the geometry up here, let me quickly get the solution here. So when does this occur? So the special incident angle is called Brewster's angle. And if the angle here between these two has to be 90, then the sum of these two has to also be 90, right? So theta sub r plus theta sub t has to be 90. Theta sub r is the same as theta sub I, that's the law of reflection. And so we can plug in here, theta sub t is also equal to 90 minus theta sub I. Your trig identity is sine of 90 minus theta is cosine. So that's cosine of theta sub I, and which again is called Brewster's angle. So in this way, we can solve for when does Brewster's angle occur. This is the equation for finding Brewster's angle. It's essentially the same exact formula as for finding the critical angle, except for it's a tangent instead of a sine. So, but despite that similarity, there are many differences. I didn't quite get a chance to run through them and make a comparison head to head of the critical angle and Brewster's angle, so I'll start Monday with that.